Hi everyone. I decided to maybe work through some of these stoichiometry problems with you, just in case you're having any trouble at all. This is worksheet 1, and I'm going to choose just a few different problems on worksheet 1 to work through. You might notice that the sheet is formatted a little bit differently than what you have on your worksheet. It's just because of the way that things got translated into the program. The first thing that I did here is I just rewrote the equation on the BCA table so that everything fits where it's supposed to. And I'm just reading through the problem now. We've got iron, we've got oxygen, and we're going to make magnetite. How many moles of iron can be converted to magnetite in this process? Well, this is a slightly different stoichiometry problem than what we've done before, because this time we're not calculating product, we're calculating reactant, but there's nothing different about what we're going to do. So we're always just going to start with writing in what we know. And we're given 8 moles of oxygen. Now, the problem is asking how many moles of iron can be converted. So really, what we're trying to solve for is what I just circled there. We're really trying to solve for how much iron do we need. So let's just start filling in this BCA table. Okay. Before the reaction starts, we've made 0 magnetite. All right. Now, I can actually write in let's just fill in the whole table here. I actually will show just how much magnetite we can make, even though the problem's not really asking that for that. But why don't we do this? All we have to do is look at how much oxygen is being used, and the coefficients between oxygen and magnetite are 2 to 1. That's the mole ratio. So for every 2 oxygen that we use, we're going to make 1 iron oxide or magnetite. Well, we're actually given 8 moles of oxygen. So we are going to make 4 moles of the magnetite. We'll make half of the magnetite than what we have of oxygen. It's a 2 to 1 ratio. So in the end, we've got 4 moles of magnetite. But really, we haven't answered the question yet. We're going to use up all of the oxygen. And now the question is, how much iron are we going to need? All right, now, we always need to work with the mole ratio. And this mole ratio happens to be a 2 to 3 ratio. So it's not as easy to do in our heads, maybe. And since it's not as easy to do in my head anyway, I'm going to set it up as a proportion. And I'm writing my proportion here. For every 2 oxygen, I need 3 iron. And how much oxygen am I given? I'm given 8. So I'm going to solve for x of the iron. So 8 oxygen, we're going to solve for how much iron we need. Okay, if I cross multiply, that's 8 times 3 is 24 equals 2x. And x will be 12. Okay, so again, all I really did here is I set up a proportion that is going to help me to solve this problem. Who knows? Maybe you can do this in your head. For every 2 oxygen, I need 3 irons. In other words, for every 1 oxygen, I would need 1.5 irons. So 1.5 times 8 would be 12. Or you can set up a proportion. There are many ways that you can look at a problem and solve it. There's my dog. All right, so I needed 12 moles of iron. I would use all 12, and then I would end up with 0. That would be the completed BCA table. But remember, all I really was solving for was what I circled there. All right, let's try number 4 on this same worksheet. All right, and again, I'm choosing this problem because we're solving for how much reactant we need. We're not solving for how much product. The first thing that we needed to do with this problem is we needed to balance it. So I just wrote the balanced equation, and now I'm going to rewrite it into the BCA table so that it all fits together. All right, so I just wrote in everything in the BCA table. We've got our balanced chemical equation. Now let's just fill in what we're given. So the question is, how many moles of oxygen gas would be needed? We're going to be solving for what I'm circling right there. That's what we're solving for. We're given 8 moles of H2S, hydrogen sulfide. Okay. All right. Again, we've got a 2 to 3 ratio here. So it's not as neat as some of the other neat ratios that we work with. We could set up a proportion. And why don't we do that? All right. So I'm just setting up a proportion. For every 2 H2S, I need 3 oxygen. All right. I'm given 8 H2S. So how much oxygen do I need? I can cross multiply. That's going to be 8 times 3 is 24 equals 2x. And coincidentally, the answer again is 12. That's just pure coincidence. But the answer is we need 12 moles of oxygen. Technically, we've solved this problem now. But why don't we go ahead and solve for the rest of it? We'll just fill in the rest of the BCA table, even though it's not being asked for. Well, actually, you know what? It is actually being asked for here. In B, how many moles of sulfur dioxide are produced? Okay, well, great. We're going to use up all of the H2S, and we're going to use up all of the oxygen. Okay, now take a look. The mole ratio between hydrogen sulfide and sulfur dioxide is 2 to 2. In other words, for every one of these, I can make one of those. All right, well, let's fill it in. We're going to start with nothing, of course, and it's a 1-to-1 ratio. So we're going to make 8 SO2s, and that'll be the answer to that question. And then the next question is how many moles of water are produced? Again, it's a 2 to 2 ratio, so we're going to make 8. And in the end, we have 8 moles. All right, I think we'll solve the last one on this worksheet. Ironically, it goes from number 4 to number 2. So we're looking at this one where it says propane burns in the presence of oxygen. One of the reasons I want to do this is because, again, we're solving for how much stuff do we need. How much propane would be burned if you made 12 moles of carbon dioxide. First, we need to balance this equation. So I'm just going to go ahead and balance it. Okay, so here's the balanced chemical equation. I put everything into the BCA table the way we need it. Now, we're making 12 moles of carbon dioxide. So remember, this is the after. So we're making 12 moles of CO2. Okay, the question is, how much propane do we need? All right, well, that's really what we're solving for, what I just circled there. Okay, now I'm just going to talk through this really quickly. Take a look. For every 3 carbon dioxides that we make, we need 1 propane. So the propane is going to be 1/3 that much of CO2. It's only 1/3. So really, to solve this problem, I'm just going to throw out the answer, but then we can work through it some more. Here's the answer. I just need 1/3 of 12. That's simply going to be 4 moles. And we've solved the problem, okay? But let's just go ahead and work through the rest of the BCA table. So we already have the answer, and hopefully you followed that. It's a 3-to-1 ratio. So if we make 12 carbon dioxides, we only need 4 moles of the propane. We're going to use up all of it. I'm assuming that this is the limiting reactant because we're not told how much oxygen we have. So I'm assuming that it's in excess. And but we can see that we would need 20 oxygens because the ratio between propane and oxygen is 1 to 5. So 1 propane for every 5 oxygens. If we use 4, we're going to use 20 oxygens. So that's, in the end, we started with excess and we ended up with excess minus 20. How much water would we make? Okay. Well, let's run through this. For every 1 propane, we'll make 4 waters. The amount of water is going to be 4 times that of the propane. So we're just going to take 4 times 4 moles is 16. And we're going to make 16 moles of water. So really we solved for everything there. We solved for the problem there immediately. The answer is 4 moles of propane. Hopefully you're getting the swing of this. And again, I just wanted to run through some problems where we're working with the reactants and not the products. It's not really anything different, but I wanted you to see how these are slightly different. Okay.